Hi, everybody. Well, if you were watching live, you would know that I started talking before I hit record, but now I just told you, so now you know. Anyways, we're going to go over today basic power supply calculations. So this is a power supply that is using a bridge rectifier, a filter capacitor, and a Zener diode network for a regulator. So we're not using the specific voltage regulator like an LM317. We're going to use this basic circuit here, and we're going to go over our calculations. Okay, so what we want is we want to have a circuit that gives us 10 volts output on the load, on a 1K load. Okay, we want to make sure our design that we're looking for is that the ripple current, the ripple voltage coming into the series resistor is no more than 500 millivolts. Okay, so we're going to call that VR in. So the ripple current on the input, and we want that to be 500 millivolts, peak to peak. Okay, so that is here. So VR in is here. So a basic power supply consists of 4 components. We have our transformer. And that is to either step down or step up the incoming voltage. In this case, we're stepping it down. We're going from 120 to 12 volts. It's a 10-to-1 transformer. We have our rectifier, and the rectifier converts AC to pulsating DC. Okay, we have a filter, and what a filter does is it helps smooth out the pulsating DC, so we have more DC and less AC. So in this case, it's just a simple capacitor. And then we have the Zener regulator. Okay, we have the Zener regulator. And that is going to regulate our output voltage. All right, so those are the basic components. All right, so when we're talking about the transformer section, what we have is, we're just going to review a half-wave rectifier and then a full-wave rectifier. Okay, so with the half-wave rectifier, what we have is we have our input signal, which is a standard sine wave. Okay, and because diodes only conduct in one direction, what we have is it is only going to conduct in the positive half of the AC wave, and the negative half will be filtered out. Okay, so what we have then is this. We have that it conducts on the positive half cycle, and then it doesn't conduct on the negative half cycle. Conducts and then doesn't conduct. So that's what we have. We have a pulsating DC. Okay, now this here is V peak coming out of the transformer. Okay, so V peak on the secondary. So we're going to say that V RMS on the secondary is 12 volts AC. Okay, we know that because it's 10-to-1. So V peak is going to be 12 volts divided by 0.707, okay, which is 16.973 volts. All right. Now, because this is coming through the rectifier, our Vmax on the output is going to be, so Vmax is going to be V peak, this peak here, minus 0.7 volts, because 0.7 volts gets dropped across the diode. Okay, so what we have here is now 16.273 volts. So that's what we have for our max. We can get into a little more complicated than this because of the negative half cycle, but we're just going to keep it like this for now. All right, so the average DC value of this pulsating half-wave rectified wave, okay, the DC value or the average value is equal to 0.318 times Vmax. Okay? So in this case, it is 5.175 volts. And that's our V average, okay, which is also what our DC voltmeter would read. Now, we still have a wave that goes up and down. So this is our Vmax, okay, and we have our V average. But if you remember, this is also a ripple voltage. This will still register as some form of AC because it is a wave, it does have a maximum and it does have a minimum. And the way we calculate that for a half-wave rectified signal is we take, so V RMS is equal to Vmax divided by 2. Okay, so in this case, it's 8.137 VRMS. Okay. So this is not a very efficient way of rectifying a signal. In some cases, it might be good enough, but if you're going to make a power supply like we're making here, you need to go in a little deeper. Okay, so for a full wave rectified signal, now we have our bridge rectifier, again, a 10-to-1 transformer. So what a full wave rectifier does is it takes your incoming sine wave, okay? It takes your incoming sine wave, and what it does is, as we reviewed before, on the positive half cycle, it is using this diode and that diode, and on the negative half cycle, it's using this diode and that diode. So it is rectifying both halves of the cycle, the positive and the negative. So what we're getting is this. We're getting that, okay? So we're getting a DC full wave rectified signal, okay? Now, with our half wave rectified signal, our cycle, here is one cycle of the input signal at 60 hertz, and one cycle of the half wave rectified is still the same length, okay? So the frequency of a half wave rectified signal is 60 hertz, the same as the incoming, all right? Same as the incoming. Now, here, for a full wave rectified signal, we have, it is now doing this cycle over half the time. So now our frequency of a full wave rectified signal is now 120 hertz. Okay, it's 120 hertz. All right. And what we have here now is on incoming VRMS of the secondary. VRMS of the secondary is 12 volts AC. Okay, so V peak, just like before, V peak of the secondary is 12 volts divided by 0.707, and that is 16.973. Okay, it's 16.973. So that is this signal here, 16.973. Now Vmax here, Vmax on that one, because it's going through two diodes, okay? Because it's going through two diodes, it is now V peak minus 1.4 volts, 0.7 for each diode. Okay, it's 0.7 for each diode, which gives us V peak minus 1.4, which is 16.973 minus 1.4, and that gives us 15.57 volts, and that is V max. So this voltage right here is 15.57. Okay? The average, or the DC value of this, so you'll see the immediate benefit of going to a full wave rectified signal, is V max times 0.636. Because it has double the average space as a half-wave rectified signal, we multiply times 0.636. And that gives us, in this case, 9.04 volts. And that is Vmax. Okay, this is before filtering. This is before filtering. Even though the peak is 15.57, the actual average of this wave, the actual average that is below these pulsating voltages, okay, is 9.04 volts. All right. Now, we still have a wave happening here on the surface, riding along the top. So there still is an AC component or ripple voltage, okay? And the way we calculate that for a full wave rectified unfiltered signal is, it is V peak or V max, sorry, V max divided by √2. Okay, it's V max divided by √2, which works out to 11 volts RMS. So our AC voltmeter would still give us some AC. So we don't have much DC, we have lots of AC. But the value we're worried about right now is this, 15.57. Because once we filter this signal, once we start filling in these gaps with the filter, okay, it is going to significantly increase. It's going to significantly increase our DC value. It's going to bring this number right up. Okay? So that is the transformer section. So now let's add the filter and the Zener diode. Okay? Let's add the filter and the Zener diode. Now, we want this to be 10 volts. So we're going to use a 1N4740A Zener diode, which is a 10 volt Zener diode. It has an internal impedance of 7 ohms. It has a maximum current of 21 milliamps, and it has a knee current of 0.25 milliamps. Okay, so the 0.25 is where the Zener diode will begin to work. You need to go past that. You just can't go right at the limit. So what we want then is we know that IRL is going to be equal to VRL over RL. Okay? And we know that's going to be equal to 10 milliamps. Because we know we want 10 volts across a 1K resistor. All right? Now, we also have to determine how much current do we want to come through the Zener diode. So let's just say we want 5 milliamps coming through that. Okay, so let's just say we want 5 milliamps. So we're going to keep that in mind for a minute. So what we need to calculate now is how much current is going to be coming in here. How much current? So now if we want 5 milliamps, if I want my Zener diode, so if I want IRL is equal to 10 milliamps, okay? And let's just say we want the current going through the Zener diode, so through D5, we want that to be 5 milliamps, okay? Let's just say that. So now, this current is 5, this current is 10, so now the current going through the current going through IRS, the series resistor for the Zener diode, is going to be the sum of these two currents. It's going to be IRL plus the current of D5, okay, which is going to be 15 milliamps. Okay. Now, here we know that Vmax from our previous screen, we know that Vmax here is equal to 15.57. Okay, we remember that from before. 15.57 volts is Vmax, which means that the maximum voltage across this resistor, we know it's 15.57 volts here. We know that the voltage across here is going to be 10 volts. So what's left here, VRS, is going to be Vmax minus Vzener or VRL, okay? Which is going to be 15.57 minus 10, which gives us 5.57 volts. Okay, so we know the current that we want coming through here. We know the voltage. So now RS, the value of that resistor, is going to be VRS, Ohm's law, over IRS, which is 5.57 over 15 milli, which gives us 371 ohms. Okay, so that's 371 ohms. So we have that all settled. Now, to calculate the capacitor, we said that we wanted 500 millivolts ripple, peak to peak, coming in here. So this is VRN, okay? So the ripple there, we're going to call that V, and it's a small r in, is 500 millivolts peak to peak, okay? So to calculate the value of the capacitor that we're going to use here, to calculate the value of the capacitor, it is going to be IRS, so the value of the current up here, divided by the frequency of the signal here, which we know is 120 hertz, times VRN, peak to peak. So it is 15 milliamps divided by 120 hertz times 500 millivolts peak. Okay, so then what we get there is 250 microfarads. So you might be saying to yourself, why don't we just eliminate all the ripple here? Why don't we just eliminate all of the ripple here, right? But what ends up happening is, suppose we wanted to drop that down to 100 millivolts peak to peak right here, okay? If we did 100 millivolts peak to peak, that means we would need a capacitor that is 1.25 millifarads. So we're talking about a big capacitor here. And it's really not necessary because a lot of that is going to get shaved off, as you're going to see soon. So what we have here now in this circuit is a 371 ohm resistor for RS and a 250 microfarad capacitor for C1. All right, so that's how we calculate that. So pause the video here if you need to write that down. And let's go see how our circuit turned out. So we're going to analyze the entire circuit now. So what do we have? This is our original circuit. We have at this point here, we have 12 volts AC. Okay, we have 12 volts AC, which also worked out to be 16.973 volts peak. 16.973 volts peak. All right, and that is at 60 hertz. That's at that point. All right, now at this point, before filtering, okay, once the capacitor is in, there is no point before filtering, it's filtered. But at that point there, what we have is a Vmax of 15.57. Oh, the other thing you need to know here is our V average. So VRMS, sorry, V peak, frequency, and our V average here is 0 volts. Okay, this is a straight sine wave. It's AC, it's on 0, so it's 0 volts. So on this side now, our Vmax, as we went over before, is 15.57. The average is 9.04 volts. Okay. VRMS, as we calculated previously, was 11 volts RMS. So there's still a lot of AC in there that needs to be filtered out. But a big switch that we have to remember is that the frequency after a bridge rectifier is 120 hertz. Okay, the bridge rectifier after a bridge rectifier, the frequency is 120 hertz. All right. Now, we stated previously that our design wanted an input ripple voltage, so it's input of 500 millivolts peak to peak. That's what our design wanted. Okay. Now, RS that we calculated was 371 ohms. Our capacitor that we calculated was 250 microfarads. Okay. So that's what we have there. Now, we know that our DC voltage coming out here is 10 volts DC. That's what we wanted, okay? And that is what our Zener regulator is giving us. But we still have a little bit of ripple. So the ripple here is known as the output ripple. Okay, so small r again, it's the output ripple. All right. Now, how do we calculate that? Well, we know, so calculate VR out. Okay, we know that the impedance, for lack of a better term, resistance of the Zener diode is 7 ohms. We know that the load is 1K. And our S is equal to 371 ohms. Okay, so what we need to do is use our voltage divider. We'll find these two in parallel, and it will be these two over the sum of RS plus these two times the input ripple, and that will give us the output ripple. Okay, so first things first, and that is the impedance of the Zener. So Z Zener in parallel with RL is 7 ohms in parallel with 1K, and that gives us 6.95 ohms. All right. And the voltage divider will be these two in parallel over these two plus RS times VR in. So the output ripple, VR out, is going to be equal to the Zener impedance in parallel with RL over those two in parallel again, plus RS times the input ripple. Okay, so that gives us 6.95 over 6.95 plus 371, and we multiply that times 500 millivolts peak to peak, and that gives us an output ripple of 9 millivolts peak to peak. So we went from, so we have here 9 millivolts peak to peak. We went from 500 millivolts to 9 millivolts, and we have a steady 10 volts DC. Okay, so we have a fairly clean signal. Now, if you wanted to make it even cleaner, then you could play around with the resistor values, redo the calculations. Okay, you could maybe put a bigger capacitor here, depending on how big you want to get. But we would, you know, if you double the capacitor, then you would have, or if you wanted half the ripple, you would double the input capacitor, which would make this smaller. But it all depends on, you know, you don't want to get too big. It all depends on how big, how much space you have on your circuit design, and if it's really that necessary. Okay, but you have to watch, because if you go too big, it starts to interfere with the operation of the power supply. So this is how we would calculate it. What we wanted was, we wanted 10 volts across the load, and we wanted no more than 500 millivolts coming into our regulator circuit. And that's how we calculate that. So if you have any questions, let me know. And I hope this was somewhat helpful. And I wish you all a great day.